Hey everyone, gonna move on to question number 2 and yes, review that one, give it a little walkthrough. So question number 2 says a discus thrower spins a discus with an angular velocity of 420 degrees per second. The distance from their axis of rotation to the center of gravity of the 2 kilogram discus is 1.2 meters. So the first question, if we look at A, is asking what is the radians per second. Okay, so we'll go back to the question, see what we know, draw a picture. Again, always a good idea to get all the details figured out visually, spatially, as well as collect our information and our data that we know. So we have some sort of a discus player or thrower. We'll be taking a vertical view, looking down at them this way. It's generally good perspective depending on the angle to look down on the paper as through the axis of their rotation, whatever that happens to be. So a discus player, of course, has their arms stretched out holding the discus. Their bodies are vertical, so their axis goes straight through their bodies. So we're going to look straight down that axis point and start from there. So again, we were cued up by seeing angular velocity, so we're thinking rotational kinematics of some sort. Okay. So they give us the angular velocity, which is 420 meters per second. So we can write that down over here. So angular velocity, 420 degrees per second, just to know that we have that. And then just as a brief review here, how does that relate to what this player or this thrower is going to do? Well, that's going to be how quickly they're going to be rotating around their center, right? So they're going to have some sort of a radius arm. How quick does that move around? The change of the angle for every unit of time, right? So it's a rate. Okay. Let's get back to it here. So again, I'll have that little center looking down at the top of the head of the thrower. They give us that rate at which they're traveling, and we'll see that the distance from their axis, so that's here, the axis point looking straight down of rotation, all the way out to the center of gravity of the discus. So essentially from their spine, through their shoulder, through their arm, all the way out to their hand. We're going to assume that's something called a rigid body, just one piece of not moving, say from the shoulder or anything. It's just one straight line. Based off of this question, we're going to make that assumption. 2 kilograms as far as the discus weight, that doesn't really matter to us right now. That's just kind of extraneous information telling us about the discus. But going back to the axis to the center of gravity, that is 1.2 meters. We've collected our information. We're now going to go from from degrees per second to radians per second. So what we'll do is we'll get our 420 degrees, and we're going to multiply that by a conversion factor. Okay. So we can look at our equation sheet first of all to try to figure out what that is. So we come on here, we take a look. Okay, let's see. We are trying to go from degrees over to rad. So to get to radians, I see 1 degree, which is what we have there, is the same as saying pi divided by 180 is rads. So to move the pi divided by 180 over to the degrees, just to show the math for that. So if I have degrees, let's pick a different color. Let's go degrees is, sorry, I'm going to write that out so it's more clear. Degrees equals, what did I say, pi over 180. And you can also supplement that if you actually punch that in your calculator, so you take pi, the pi button, divided by 180, it actually gives you 57. That is supposed to be a 5, believe it or not. 57.3 degrees. Okay, but we also have this rad here. Okay. So what we do with that is, again, we want to move this concept, or move this component over because we're trying to solve for that. So we divide both sides by pi over 80, or another way of saying the exact same thing is dividing both sides by 53.7. Okay. So either way, we're gonna get something that says degrees equals, or divided by either one of those two terms. So let's just say 57.3 to make it look easier, equals our new units of radians. Okay. So if we go back to our equation with this in mind, we got 420, so that's our degrees, divided by 57.3 equals, when we punch that into calculator, 7.3 rads per second. Okay, and that unit's important because we're talking about angular velocity. Okay, great. And we can do a little concept check here, which will be really helpful, I think. So what does it mean, and what would it look like to be traveling at 7.3 radians per second? Well, we have our center of axis here, we have our radial arm, and right. So if you recall, one full circle as we're traveling around is equal to roughly, again, it's not exact, it's a little bit more, but 6 rads. Okay, because again, if you remember, 1 radian is your radius, but it's laid out along the circle. Okay, so what that means is that would be 1 radian traveling along. Again, it's the same length as from the center of the circle to the outside. So that's 2, that'd be 3, 4, 5, and 6. Okay, that's obviously not a perfect circle, but that's the premise. Okay, so we get roughly 6 radians for 1 full circle. So if we're saying this discus thrower is throwing a discus at 7.3 rads per second, what we're really saying is this person does 1 and a bit rotation from start to finish every second. So for every unit of time, for every second that passes, they're rotating around that axis 1 and a bit times. Okay, so that's really, really fast. This makes sense if you see a discus thrower or hammer thrower right at the very end of their throws. Okay, so good concept checked. Here we are. That's our answer there. Okay, so let's keep moving forward. So we have all the same information as we did before, but this time now the question is asking something new. Okay, and it's asking for linear velocity of the discus. So again, a little bit of a concept check here will be helpful as we're getting into this, and it'll actually give us our answer more or less. But if we were to have our discus thrower here again, or let's say any object, in the lecture slides we have a record. So you have a record that spins around the center at some sort of a angular velocity. So again, it's always rotational or turning in radians or degrees if you want to think about it, to give us our change in placement over time for our angular rotation, right? Angular Rotation is change in angle, which we can think as angular displacement over time. Okay, but on that same record, what the example is there's a fly, right, sitting there, and so what it's trying to relay is that even though there's some action spinning happening at the center, what happens along this radial arm is that the fly at the outside is only experiencing a velocity perpendicular to what's actually occurring on the spinning on the inside. And so other places that you might experience this is if you were to hold on to, let's say, even a crumpled ball of paper or something like that. And you hold it with an outstretched arm. As you're spinning around at the end of your hand, if you all of a sudden just let go of the paper, that paper doesn't keep rotationally spinning around you as you let go of the paper, right? It has a linear velocity as soon as you let go. So somewhat of a similar idea is the concept of this fly. If the record were to just spin so fast that it couldn't hold on anymore, the fly would literally go flying off, but in a linear direction perpendicular to the rotation, right? The rotation is kind of happening. Oh, I have that going the wrong way, sorry. So if the velocity is occurring that way, the rotation of the center would be around that way, or angular velocity, or angular displacement, or change of position, right? Okay, so hopefully that'll get a little bit of a deeper understanding as we answer question B. So what is the angular velocity? Again, velocity is a rate of some sort of a change of displacement, in this particular angular, over time. Okay, so if we go back to our equation sheet here and we take a look around, anytime we're dealing with angular motion, we want to try to see a change of degrees or radians in this case. So we're going to look at all our equations here, and okay, generally speaking, we see some angles here, but we know that's for our angular velocities when dealing with projectile motion. So we arrive at the tail end here where we're dealing with angular or rotational motion. Okay, so it's asking for, we know angular velocity, and we remember that the weird W omega sign means angular velocity. So we have 1, 2, 3, 4, 5 equations with it in. So what else do we know here? Well, again, we have our angular velocity equaling 7.3 rods a second. What else do we know? We know we have some sort of a radial arm, as we said here, that's 1.2 meters long. And what we're looking for is angular velocity, which is represented, as we know, with just a v. Or sorry, linear velocity, which we're familiar with from that we've been working with in all our other units. So velocity, but we don't know what that is. Okay, so we need some sort of an equation that has angular velocity, radial arm, and of course our unknown, which is velocity. So we go back and we take a look here. Okay, well, we actually have a couple by the looks of it. There's one, velocity, so linear velocity equals the radial arm times the angular velocity. That sounds like the one, but just to be thorough, we have angular velocity equals linear velocity over a radial arm. So these two equations are just rearrangements of each other, but we're solving for linear velocity, so we want to use that one. Okay, none of the other equations give us that with what we're looking for. So this becomes a lot simpler of a question. You know, it's a little bit more of just a plug and play with this one now. So again, we'll look at our V equals angular rotation, and that makes sense. We'll get to the concept in a second, times the radial arm. So once we plug that all in, that equals 7.3 times 1.2, right? And that equals 8.76, or if we're just going to one decimal place, 8.8. And again, when we're dealing with velocity, in particular linear velocity, that's meters per second. Okay. So again, just a little concept check-in on that. So what we're saying is, as the discus thrower is spinning around, we'll get rid of the fly. We'll actually make this to the system that we're talking about now. Okay, so let's get rid of that. Okay, here's our discus thrower. As they're whipping around, okay, so maybe starting in this position, here's their hand, that's the discus. So they're gonna whip around at an angular velocity, that's a W, of, where'd it go? There we are, right in front of me, 7.3 rads per second. Okay, so I'm gonna rewrite that just so it's a little clearer. Okay, so angular velocity is 7.3 rads per second. Great. So we know that. That's the speed of this. We're saying the change in the angle expressed in rads per second. Every second is that. Okay, great. So now what we're going to get to is that's going to keep occurring all the way around to some point, and it's not necessarily saying that they're throwing and letting go of it, but I think conceptually this helps. That when they get to some point, let's say here, not that they are letting go, but if they didn't let go, they'd keep continuing around the circle. But if they did let go, what would happen is the discus would shoot off at the same, or at a linear velocity that is equal to the length of the arm. So radius, the length of the arm, that's this one, 1.2 meters, times, so it's proportionate to the angular velocity. And of course that gives us this catapulting discus potentially off into the air at a linear velocity of 8.8 meters. Okay? That's all it's saying. And again, if they were to keep hanging on to it, that doesn't mean the discus isn't experiencing a linear velocity at that point in time. It's just experiencing that velocity while continuing on with rotational movement. If we were to let go, then the linear velocity would also be at that moment 8.8 meters per second.